I think you people are seeing the video lectures also. Akansha Devedi,
Yes, sir.
have you seen the video lecture which has been uploaded on the YouTube?
No, sir, I have not watched any lecture, but I have seen all the topics there.
Okay, but you should you may rewind the lecture. For example, if you have any doubt, and you should have the repetition of the same thing key at this point what I have spoken and what the explanation is there. And especially the student who has not attended the classes by any means, either due to the network problem or their problem at their own end, then they can see the YouTube lectures there, because I used to record it, and as such I used to upload it on the YouTube. And I also used to give the link for the same on the WhatsApp group. Uh, I think the link what I have shared on the WhatsApp group, have you seen that or not? Amrita Gupta,
Yes, sir.
have you seen that? Na?
Yes, sir. I have seen that.
Okay. So if you open, then have any problem in running that videos, or you're
No,
comfortable
sir.
with that
No,
or no?
sir. I'm
No problem.
comfortable with that. No, sir.
Okay. So anyway, just I was taking the feedback for that. So today is still the center of uh, mass is
Sir,
not the point of discussion. Huh,
sir,
Dharani?
yes. Sir, I was reading the PDFs which you have sent and the lecture you took. There was one of the example in that
Uh-huh.
with the note which you shared, which was the handwritten note. So
Okay.
there the sign convention was different, and
Okay.
the one you taught us in the lecture
Uh-huh.
was there the example was mentioned and the sign convention was different, so
Okay.
I was confused. So but when after that I got to know that the written note was right, and maybe that was a typo mistake, so I just thought of confirming that.
Okay, actually, what happens sometimes, no, if anything I'm writing there, maybe that something has been mentioned uh, mistake by mistake. But whatever the thing I wish to communicate you people, no, whatever the convention of sign is there, no, that is the relative thing. And if you are considering one side as the positive, then the opposite to that should be considered as the negative, especially in case of these forces as well as the torque, whatever you are considering there. Usually, we used to take it a left-hand side and a right-hand side. And according to that, we justify the sign. But anyway, if you have any problem when you will come offline, then we will see all those things. So today I'm going to discuss the lecture number 24, where the motion under central forces is still I'm escaping from the center of mass and laboratory frame of reference. But some point of discussion will be mentioned here, but later on I will discuss in detail about that. So here's motion under central force. Actually, this is the big issue related to this universe, is starting from the tiny particle like the electron and nucleus to the giant particle like the planet and the stars also. And you will see that in all the cases, the motion is governed by a central force. So many examples you might have seen in case of the electrostatic as well as in case of gravitation. But that can be extended to almost all the issues there, in which the condition of the central force is fulfilled here. So that's why we are taking this topic uh, as a matter of discussion in this lecture. Ki what are the central forces and how the motion is convened under the central forces? What are the limitations to that? What are the equation of motions to that? And how we used to consider the same for its extension in all those where such type of forces are acting. Either we are discussing about the motion of the planet around the sun, or we are talking about the body which is under the influence of gravity, or any other thing, whatever like to that, we have to discuss, and we have to uh, write the equation for the same, so that that can be extended and applied to almost all the type of such motions in which the conditions of the central forces are fulfilled. So let us see what are the things there, what I wish to discuss here. We have already met the central force problem in both electrostatic and gravitation. By electrostatic, in the case of electrostatic, uh, what about the force of electric field that is uh, that is from a particular point to the outward direction, or from outward direction to the directed to a particular point. So this is in the category of the central forces. Similarly, gravity itself attracting the things towards itself, that under the gravitational force all the motion is also on the same type, that is the central force problem. A key point that governs the behavior is that there is no transverse force, hence the angular momentum is conserved. This is very important condition for the central force. Later on we will see also how this fulfills there. This is only strictly true for two bodies, and for spherically symmetric masses are the charges. You might have seen in most of the cases, if we are discussing the problem related to electrostatic, then the charges are considered to be spherically symmetric. And as well as if you are talking about the giant particle, big particle like the planet and stars, then in that case also almost the same situation is prevailing there. That's why the main condition for the central forces where we are going to discuss, there should be two body, means that the problem which we are going to describe under the central forces are the two body problem, and the bodies are usually of the spherically symmetric mass are the charges. If we are talking about the masses or we are talking about the charges, then that should be spherically distributed. So as soon as the third body added, that is not on the line between first two, a transverse force appears here, and hence this deviate the main issue what we are discussing under the central forces. Means that there should be two body. If the third body is there, then that should be between the line of action of these two bodies. And if it is beyond to that, then there will be another cause of the transverse force which appears and will deviate from the conditions of the central forces in that case. And even bodies are nearly spherical as the Earth and Moon, nevertheless exert the tidal forces that cause an exchange of momentum. That's why already we have stated there, in this condition, the angular momentum is almost conserved there. But the well-separated planets and stars interact in an excellent approximation through two body central forces, as do a proton and electron in case of the hydrogen, are in diatomic molecule. Means that if you are seeing here that the well-separated planet and a star means if you are considering the solar this solar system of this universe, then sun can be considered as a star, and other planet which are revolving around to that have just the nice example of the central forces. And here we have two bodies, and the line of action between that, or the force between them, are exactly in the same condition as the central force required there. And If you will come to the tiny particle like the electron and proton, then the same situation is again prevailing there. Then these are the nice example of the central force problems. Even when the quantum effects are important, those effects are described in the language borrowed from the two-body central force problem. So this is an important problem to study. That's why we are very much focused and concentrated, especially in case of the central force problem. And in most of the cases, if we are dealing with the Newtonian mechanics especially, then the things are visually appearing to us. Either we are talking about the planetary motion or we are talking about the electron motion. Then although it is not possible to see the electron by our naked eye, but in it is as usual, as we used to say that it is the usual phenomena and usual particles which are under discussion under the central forces are there. For definiteness, we will restrict ourselves to the gravitation problem, but keep in mind that these ideas apply directly to all central force problems. Hence that I'm going to discuss the gravitational problem. Why gravitational problem? Because in that case, visually, laterally, we are seeing the things there. And which is one of the important criteria of the classical mechanics or the Newtonian mechanics. What happened actually, if the things are appearing to us, then it is very easy to visualize that. इसीलिए जो मैकेनिक्स के लॉज आए वो सबसे पहले आए, क्योंकि जो चीजें विजुअली हमें दिख रही हैं वो हम उस पर लॉज बना सकते हैं, उनको रियलाइज कर सकते हैं, उनको डिपिक्ट कर सकते हैं. लेकिन जो चीजें किसी इंस्ट्रूमेंट की सहायता से देखी जानी है उनको देखने में हमें दिक्कत है, इसलिए हम इन आइडियाज को बारो करेंगे और बारो करके उस चीज पर लगाएंगे, देखेंगे उस वर्ड में ये हमारे जो लॉज हैं वो एप्लीकेबल हैं या नहीं है. तो व्हाट हैज बीन रियलाइज दैट द problem what we deal under the gravitational force that have the same essence as we discuss the issues related to electron and proton at the case of hydrogen, or you can say that the particles which are interacting at the nucleus level also. So well, we will deal the problem under the gravity, and we will extend all these issues, equation and theory to the all particle in which the central force laws are fulfilled there. Central force laws are fulfilled means that the force between these two particles, those two particles, either they are the tiny particle or they are the charged particle or they are in the other world of quantum mechanics, if they are having the condition of the central forces acting between them, then we can apply freely all these equations and these theories to those problems also. Okay, so that's why we are starting from the gravitational problem of two bodies. So as usually you are studying it from the class of 9th, 10th, that if we have two gravitating bodies of the masses m1 and m2 at positions r1 and r2, the potential energy can be given as u r11 is equal to g m1 m2 upon r1 minus r2. We have taken the mod of that in the denominator, and it is also have the negative sign also there. So negative sign shows that there is force of attraction between them. And there is the mod value that is important here that we will describe here later on. A key point is that this depends only on the separation between the masses, not on R1 and R2 separately. Acha, what is R1 and R2? Let me know what you are thinking and feeling, visualizing for the R1 and R2 related to the M1 and M2. Can you tell me about this one? What is R1 and R2?
So position of mass m1 and mass m2.
If you are talking about the position, then almost you have to take the reference for the same, no?
So from origin like
From origin.
whatever the reference
So
I'm taking.
from a particular fixed point, from particular origin, whatever you have considered, that you are uh, taking the position vector of M1 and M2, means that where they are lying in the space. Until you will have a fixed point to have their position, you cannot measure what is the relative difference between them. So that's why R1 has been taken as the position vector of M1 and R2 as of M2. And if we will take the difference of that, and that difference in the positive value, that is the mod value of the difference of R1 and R2, then we will write it in the denominator of the above expression. Thus, the system is translationally invariant. In addition, if the in addition, if a conservative force is central, then U is independent of the direction of R1 minus R2 as well. Just I am talking about this thing that are translationally invariant. So anybody you can tell me that what do you mean by the translationally invariant? What it means, what it refers. अगर हम कहें कि ये ट्रांसलेशनली इनवैरिएंट है, इसका क्या मतलब हुआ?
कांस्टेंट मोशन से मतलब वो
कांस्टेंट मोशन मींस कांस्टेंट मोशन का क्या मतलब हुआ? जैसे
एक्सेलरेशन 0 होगा।
यहां पर क्या इसका सेंस है? ट्रांसलेशनली इनवैरिएंट का यहां जो मतलब है, एक्चुअली जो M1 और M2 के बीच का डिफरेंस है डिस्टेंस का, वो अगर डिस्टेंस आज सच कहीं चल के चला जाए, यानी वो डिफरेंस एज सच चले, यानी जितना R1 चले उतना R2 भी चले, यानी उनके बीच की जो कांस्टेंट डिस्टेंस है अगर वो फिक्स है और वो कहीं भी चली जाए इनवर्स में, तब भी उन दोनों बॉडीज के बीच का जो फोर्स होगा या उनके बीच का जो पोटेंशियल एनर्जी होगी वो उतनी ही होगी, वो वेरी नहीं करेगी। यानी ड्यू टू द ट्रांसलेटरी मोशन ऑफ द डिफरेंस ऑफ the distance between M1 and M2 moving anywhere in the universe. But the condition is that the difference should be constant, that the constant difference is having the translatory motion in the universe, then at all the time, at every places, the potential energy remains constant, invariant. This is the meaning of this one. It depends only on the magnitude of R1 and R1 minus R2, that the mod value of that. Thus, we can write it as that the potential energy R1, R2 can be written in better form. That is the U, that is the function of the mod of the difference of the distance between M1 and M2 there. To make the thing simpler, they introduce a new variable, that is the R. What is the only the difference between R1 and R2, which is the position of body R1, body 1 relative to the body 2. You depends only on the magnitude of R, and hence obviously you can say that the U is equal to UR. In terms of the Lagrangian mechanics, we have for the two body problems, what we used to write that L is equal to T minus U. So T minus U means that you are taking the kinetic energy corresponding to these two, that is the half M1 R1 dot square plus half M2 R2 dot square minus U. This is the Lagrangian for the system what we are taking here, or you can say half M1 V1 square plus half M2 V2 square minus UR. This is the idea about the center of mass or the relative coordinate and the reduced mass. Although these things we will discuss with the applied aspect later on, but the idea about the center of mass and then the relative coordinate and the reduced mass. What it refers, let us see here. The position vector of a center of mass is defined as the R is equal to M1 R1 plus M2 R2 upon the total mass, that is M1 plus M2. And this is equal to M1 R1 plus M2 R2 upon M. R usually you can say 1 upon total mass समेशन ओवर आई एम आई आर आई, यानी जितने भी पार्टिकल हैं, अगर हम और भी पार्टिकल्स लिए हुए हैं, 3 पार्टिकल हैं, 4 पार्टिकल हैं, तो उनकी रिलेटिव डिस्टेंस क्या है देयर, और उनका अगर हम टोटल मास से भाग दें ऐसे मल्टीप्लाई करके, then we will have the position vector of the center of the mass, and that can be defined here. Here strictly we are saying that we have only 2 body, because the central force problems are usually discussed for the 2 bodies. So that's why we are taking M1 and M2 here. As we know that the center of mass is along the line joining the 2 masses, and the distance of the masses from the center of mass is in the ratio of M1 and M2. Whenever you will talk about this one, कि center of mass अगर हम 2 मासेस लिए हुए हैं, तो उनके बीच में कहीं उनका सेंटर ऑफ मास पड़ेगा जो उनको लाइन ज्वाइन करेगी, और वो ये निर्भर करेगा कि वो किधर कम है या किधर ज्यादा है। ये बात यानी उस सेंटर ऑफ मास M1 की तरफ पड़ेगा या M2 की तरफ पड़ेगा, उसकी डिस्टेंस क्या, ये दोनों इस बात पर निर्भर करता है कि M1 M2 की क्या वैल्यूज है। If M2 is far greater than M1, for example, then the center of mass is very close to body 2, and vice versa also. The total momentum of 2 bodies is the same as if the total mass were concentrated at the center of mass location and following the motion of the center of mass. That's why you might have read it. If you are not have seen it, then we will discuss in the next lecture, maybe next lecture, ki how the center of mass and laboratory frame of reference, these are related to each other, and how the motion is considered in case of the center of mass. Actually, in the center of mass, what happened actually, the center of mass as a whole is moving there, and usually in such type of frame of references or in such type of system, the momentum is conserved there. So we will realize there. That's why here, if we are talking about the momentum of that center of mass, then M into R dot, that is MV, P is equal to MV. R1 and R2 in terms of R in center of mass and relative position R are given in terms of this one. That is the R1 is equal to capital R plus M2 upon M capital M plus into R. Similarly, if we are writing it in terms of R2 in terms of capital R and R, then that is R minus M1 upon capital M into R. If we will calculate it using the earlier equations, then you can find this particular relation between R1 capital R and R2 capital R and small r. So if we will take the differentiation with the respect to time, then R1 dot is equal to R dot plus M2 upon capital M into R dot, and similarly R2 dot is equal to R dot minus M1 upon capital M into R dot. Putting these values in the kinetic energy expression, we will write it as T is equal to half M1 R1 square R1 dot square plus half M2 R2 dot square, by putting the values of R1 dot as well as of R2 dot in the wave equation from the earlier expression what I have written there. Then what we will get actually, half M1 within bracket capital R dot plus M2 upon capital M into R dot to whole square. Similarly for the other term, the square term along with the half into capital M2. Multiplying the squares, we find the cross term cancel, and we have left with the simple result, that is T is equal to half M capital R dot square plus half mu R dot square, where mu is the reduced mass of the system. That is, we have M1 and M2, then they have the reduced mass, and where the symbol M means that the mu is here. Mu has been used for the reduced mass. This will be the mu, not the M here in this equation. So let us correct it here. Better to correct right now, otherwise it will be left. So what we are discussing here, that for the symbol mu has been used for the reduced mass, and this reduced mass is equal to M1 M2 upon M1 plus M2. This is an important quantity that you will see again, so you should get used to it. Another way to write it as that 1 upon mu is equal to 1 upon M1 plus 1 upon M2. Note that mu is less than the smaller of M1 and M2. इसका मतलब कि जो mu की वैल्यू होगी यानी reduced mass की वैल्यू होगी M1 और M2 में से जो छोटा होगा उससे भी छोटा ही होगा, उससे कभी ज्यादा नहीं हो सकता है. और आप अगर आपके पास अगर इसकी आइडिया लगाना हो तो मान लीजिए हम M1 को 1 रखे हैं, M2 को 2 रखे हैं, तो बताइए भाई म्यू की क्या वैल्यू होगी? आकांक्षा बताओ तो क्या होगा? M1 इज इक्वल टू 1, M1 इज इक्वल टू 1 है और M2 इज इक्वल टू 2 है, तो क्या हो जाएगा? क्या होगा?
सर 2/3.
2/3 और 2/3 की न्यूमेरिकल वैल्यू कितनी आएगी? ऑलवेज लेस देन 1.
0.6 के
0.6
आसपास.
मैंने that is less than 1. That is less than 1. That's why what I was suggesting you people कि mu is less than the smaller of M1 and M2. यानी हमने एक की वैल्यू 1 लिया था और दूसरे की वैल्यू 2 लिया था. जो जब हम रिड्यूस्ड मास की वैल्यू निकाले तो ये एक और दो में से जो छोटा है उससे भी छोटा है. That's I was interested to clear you people. So it has the dimension of the mass and the range from M1 when to M2. ये थोड़ा सा गलत लग गया है. It has the dimension of mass and the ranges from M1 to M2. M1 to M2. Here when will not be here. Here need not to write the when. So you will see here again the things that it has the dimension of the mass and ranges from M1 to M2 when M2 is tending to infinity, and is M/2 when M is equal to M1 is equal to M2. So you can put it there equation and you can write that. जैसे M2 अगर infinity हुआ तो दूसरा term 0 हो जाएगा. 1 upon mu is equal to 1 upon M1. तो obviously ये जो है इस तरीके से चेंज होता रहेगा M1 या M2, जिसकी वैल्यू हम जो रखेंगे उस वैल्यू के हिसाब से उनकी शिफ्टिंग हो जाएगी कि म्यू की क्या वैल्यू है. Thus it tends towards the lower of two masses. The reduced mass of the Sun-Earth system is almost exactly the mass of the Earth itself. यानी उसमें जब हम reduced mass की बात करते हैं तो चूंकि सन का मास बहुत ज्यादा है in comparison to the Earth का, तो इसकी शिफ्टिंग अर्थ के मास की तरफ होती है. Returning to the Lagrangian, we now find that this L is equal to T minus U, and that is equal to the half of m r dot square minus half of mu r dot minus ur. Actually, this equation has been written in the reduced mass system, yani center of mass system. So what we are getting actually here equation you are getting that the first part is corresponding to the uh, center of mass and other is in the relative system. In the relative system, that's why LCM and LREL has been mentioned here. CM and relative coordinates are make good generalized coordinates and split the problem into two parts. And how means you can solve this by how having the L in the relative coordinate system and L in the center of mass system. With the Lagrangian L is equal to T minus U is equal to half mr dot square plus half mu r dot square minus ur, we can now write down the equation of motion. The center of mass equation is trivial and that is usually written that mr double dot is equal to 0. That is r dot is constant. What that's why what I will is telling in the start of very beginning that m into r dot, it means that the momentum of the particle in the center of mass system and that is constant. So if you will see here, then mr dot is equal to constant. That is one of the requirement of the center of mass frame of reference, and hence the CM equation trivially can be written as mr double dot is equal to 0. It should this should be no surprise because recall that our two body problem is an isolated system. Hence, no outside force are acting. That is the Newton's first law resemble to that condition here. Another way of looking at it is that the Lagrangian does not depend on capital R, which expresses a conservation law, that is the conservation of momentum there. And above point can also be stated that the Lagrangian equation of the motion for three generalized coordinate of r will not contain the terms of r and r dot. ये एक्चुअली जब हम इसको जनरलाइज कोऑर्डिनेट में लिखेंगे, थ्री जनरलाइज कोऑर्डिनेट में आर की टर्म में लिखेंगे, तो ऑब्वियस सी बात है कि उस सिस्टम में आर वाला पार्ट नहीं होना चाहिए, या हम यूं कहें कि ये हमारा आर डॉट या आर वाला पार्ट, अगर इसको हम ऊपर वाले में से रिड्यूस कर दें, जो ऊपर वाली इक्वेशन एल इज इक्वल टू टी माइनस यू इज इक्वल टू हाफ ऑफ एम आर डॉट स्क्वायर वाले में है, तो पहला टर्म खत्म हो जाएगा, केवल दूसरे वाले लेग्रांजियन इक्वेशन का पार्ट बचेगा. Hence, to discuss the motion of a system, we can drop the first term of the Lagrangian, and finally L is equal to T minus U is equal to half m r dot square plus half mu r dot square minus u r can be written as, or it can be reduced as L is equal to half of mu r dot square minus u r. The Lagrangian equation for the other coordinate, the relative position r, gives the separation equation of the motion. Separate equation of the motion, and that can be written as mu r double dot is equal to minus del uvr ur. This is the equation of motion for a single free particle of mass m. Here in case of situation that if reduced mass we are considering, subject to potential energy ur. In this case, two stars, for example, neither one orbits the other, but rather they orbit their common center of mass. Nevertheless, we can treat the problem as if a single star of reduced mass m where arbitrating at a distance r is equal to r1 minus r2 from the other fixed unmoving star. And note that either a star can be fixed one, not just the more massive one. Actually, whatever has been stated in this particular bullet point, I'm just showing a particular figure and that you will have the clarity for that. Since we have seen the velocity of center of mass is constant, we can change the frame moving with this constant velocity so that in this alternate inertial frame of reference, r dot is equal to 0. In the center of mass frame, the Lagrangian is just L is equal to half mu r dot square minus ur, and the problem is reduced to one body problem. It is important to understand this pseudo single body system, and for that, what the figure what I was telling you people here. Let us consider here M1 and M2. These are two masses, and that have their relative distance, or you can say that their respective positions are at the distance r1 and r2 from an arbitrary origin what we have considered. So what happened actually? Let us see here. If we are considering that the center of mass, then you will see that the center of mass, if it is at the distance r1 from the m1 and r2 from the m2. So usually you can realize here from the distance point of view that m1 is of the lower mass. If this situation is prevailing here, then you can see here that again this motion that this is the another position of this one. This is another position of this one. So means that the r1 and r2 are translationally invariant here. यानी इन दोनों के बीच की डिस्टेंस जो रिलेटिव डिस्टेंस है वो नहीं चेंज हो रही है, भले ही इनका मोशन हो रहा है. तो what is here actually? You will see here that the center of mass, and you are considering the distance r1 at which the m1 is lying there. Then you can take the radius r1, and this m1 is arbitrating about the center of mass. Similarly, you can consider the r2 distance, that is r2 radius, and this around the r2 radius, this is again the arbitrating here. That m2 is arbitrating here, having this center of mass. And just the distance between these two, that is the r is equal to the relative distance between r1 and r2, and mu is here as the reduced mass of these two. So what I'm interested to discuss here, जो हमने उधर उस बुलेट पॉइंट में रखा था कि भाई पहले तो m1 और m2 r1 और r2 डिस्टेंस पे है. अगर हम इनका सेंटर ऑफ मास कंसीडर कर लिए तो सेंटर ऑफ मास कंसीडर करते हुए ये सेंटर ऑफ मास किसी एक मास को के अराउंड आर्बिट्रेट करते हुए या सेंटर ऑफ मास के अराउंड वो सिंगल बॉडी आर्बिट्रेट करती हो, तो इस तरीके की सिचुएशन को हम हैंडल करेंगे, या यूं कहिए कि ये टू बॉडी प्रॉब्लम को हम वन बॉडी प्रॉब्लम में रिड्यूस कर लेंगे, कंसीडरिंग द रिड्यूस्ड मास ऑफ द टू बॉडीज हैविंग द सेंटर ऑफ मास फ्रेम ऑफ रेफरेंस कंसिडरेशन. ये बात थोड़ी सी यहां लिखने की भी कोशिश की गई है. द सिंगल बॉडी इज ऑफ द रिड्यूस्ड मास m and the center of its orbit is the other body, not the center of mass. जैसे हम ये कहें कि भाई the reduced mass, जैसे हम ये कहें कि reduced mass m है, या यहाँ पर आपने जो रिड्यूस्ड मास सेंटर पे ओ रखा हुआ है, ओ पर सेंटर ऑफ मास है, तो ये किसी एक बॉडी को सेंटर मान करके उसके अराउंड आर्बिट्रेट कर रहा है। यानी R1 रेडियस का एक पाथ आपको दिख रहा है, वो जो कि M1 को सेंटर मान रहा है या M1 को फोकस कर रहा है। ऐसा नहीं है कि जो है दूसरी बॉडी को फोकस कर रहा हो, यही बात इसमें लिखी है। द सिंगल बॉडी इज ऑफ द रिड्यूस्ड मास and the center of its orbit is the other body, not the center of mass is there. This is true even though the choice of origin that led to the above Lagrangian in the center of mass. Note that if M1 is tending to infinity, then M2 is tending to the reduced mass, and this becomes more accurate. तो इसको थोड़ा समझने के लिए एक जो जैसे उपाध्याय की किताब है सेंट्रल फोर्स वाली, सेंट्रल फोर्स मोशन का, उस चैप्टर को थोड़ा एक बार पढ़िएगा तो हो सकता है कुछ चीजें और आपको समझ में आए। नहीं समझ में आएंगे तो इसको आपको जो भी डाउट होगा आप बताइएगा, एक बार फिर हम डिस्कस करेंगे। Let us have the central force and the motion in plane. If a force act on a particle in such a way that it always directed towards or away from the fixed center and its magnitude depends only upon the distance r from the center, then this type of force is called the central force, which already I have described in the story variable. Thus the central force is represented by the capital F is equal to the function of r and into the unit vector, or you can say that it is the f r and the vector r upon the mod of the vector r, where fr is a function of distance r only and unit vector is equal to r upon r is a unit vector along r from the fixed center. The force is attractive or repulsive, that depends that this function fr is less than 0 or it is greater than 0 respectively. A central force is always a conservative force, and if V R, this is the potential energy, is the potential energy, then we can write this Fr is equal to negative gradient of potential, that is the minus del V upon del R, or F is equal to this vector F is equal to minus del V upon del R into vector R divided by the mod of that vector, means just the unit vector has been taken here. The potential energy for the central force depends only on the distance r, and hence the system possesses the spherical symmetry. Thus, any rotation about a fixed axis will not have any effect on the solution, and hence angle coordinate for rotation about a fixed axis must be cyclic. This result is the conservation of angular momentum of the system, that is J is equal to R cross P, that is equal to constant, because it is one of the essential condition of the center of the frame of reference in which the linear momentum was conserved. Here this is the here what we are angular momentum of the system is the conserved here. So J is equal to R cross P, that is equal to constant, that is the vector, where P is the linear momentum. So taking scalar product with R in the above equation, we have the R dot J is equal to R dot R cross P, and R cross P into dot is equal to 0, because in such cases dot and cross product, the position of the cross and dot can be interchanged. So that's why if you are writing the vector r cross vector r, then that will be 0, because the curl of the same vector, curl of the cross product of the same vector. Cross product means obviously if cross product means sin theta means अगर उसी direction में होंगे तो that will be 0. तो r cross r is equal to 0. Therefore, the position r is always perpendicular to the constant j vector. This means that the position of the particle under central force takes place in a plane, and we can describe the instantaneous position of the particle in plane polar coordinate, that is r and theta. So this was all about what I was interested to discuss today related to the central force motion, and some part is left here. I will discuss this in the next lecture. What is the equation of motion in the central force? Now we will derive certain equation of motion using all these things what already have uh, perceived here in the discussion during the different aspect related to the central forces. And we will see that how the motion is possible there and how are the constraint for the motion related to the um, particle under the central forces. So this was all about what I was interested to discuss today. If you have any problem, please let me know.